Everyone, today we are discussing general organic chemistry in that Frontier Molecular Orbital Theory. The theory of Frontier Molecular Orbital was proposed by the scientist Kenichi Fukui in 1951, and also he got Nobel Prize for that. We all know that Frontier Molecular Orbitals. So what are Frontier Molecular Orbitals, how the reaction will occur, and how the Frontier Molecular Orbital will interact during the product formation, we can discuss in this session. Basically, before going to Frontier Molecular Orbital Theory, we all know that Molecular Orbital Theory. We all know about MOT, Molecular Orbital Theory. In that, the Molecular Orbital Theory basically works on atomic orbital combination. According to Molecular Orbital Theory, what we can say, atomic orbitals of two molecules combine to form molecular orbitals. So atomic orbitals will combine together to form molecular orbitals. We have also know that there are two types of molecular orbitals. One is bonding molecular orbital, and another one is anti-bonding molecular orbital. In bonding molecular orbital, there are sigma and pi. In anti-bonding molecular orbital, sigma star and pi star. We also know that electrons will occupy molecular orbitals according to FMOT principle, Pauli exclusion principle, and Hund's rule. Right? The occupied orbitals stabilize the molecule, while anti-bonding orbitals are destabilize the molecule. We also know that the rule of the MOT. Right? Now we can discuss about Frontier Molecular Orbital Theory. So what is Frontier Molecular Orbital Theory? It discusses about Frontier Molecular Orbital Theory discusses about two molecular orbitals. One is HOMO and another one is LUMO. Frontier Molecular Orbital Theory discusses about two molecular orbitals. One is HOMO and another one is LUMO. So what is HOMO? HOMO is highest occupied molecular orbital, and LUMO is lowest unoccupied molecular orbital. HOMO is highest occupied molecular orbital. LUMO is lowest unoccupied molecular orbital. Consider A and B. Consider two molecules, that is A and B. So Frontier Molecular Orbital Theory tells that a HOMO of one molecule will interact with LUMO of another molecule, which will form the product. A HOMO of one molecule will interact with a LUMO of another molecule, and by their product will be formed. Most importantly, these orbitals are having boundaries between occupied and unoccupied energy levels. Hence, these HOMO and LUMO are called as frontier molecular orbitals. The interaction between HOMO LUMO determines chemical reactivity, bond formation, as it discusses about bond formation, also discusses about bond dissociation. That means bond breaking. Regioselectivity, most importantly, regioselectivity and stereoselectivity. Regioselectivity and stereoselectivity. We can highly look the regioselectivity and stereoselectivity in pericyclic diacetyl reaction, pericyclic reaction, sigmatropic reaction. In pericyclic chemistry, we can see the regioselectivity and stereoselectivity. Pericyclic chemistry. More importantly, HOMO-LUMO concept is helpful in pericyclic chemistry, and also it discusses about reaction rate, how the reaction will occur. Reaction rate is nothing but how fast the reaction will occur. It also discusses about that. And what main characteristics of HOMO-LUMO will be? Main characteristics of HOMO-LUMO HOMO and LUMO. We have the main characteristics of these two. HOMO is nothing but highest occupied molecular orbital. It is also called as highest energy molecular orbital. It is having highest energy molecular orbital. LUMO is having lowest energy. HOMO contains valence electrons of the molecule. It contains valence electrons of a molecule. It is vacant. And as it contains electrons, it will behave as nucleophile. It will behave as nucleophile and donates electrons. As nucleophiles are donating electrons, similarly HOMO will also give the electrons to the electron deficient species. LUMO is, as HOMO is nucleophilic behavior and LUMO is having electrophilic behavior, and it will accept electrons. HOMO donates electrons, LUMO accept electrons. In HOMO, easier electron donation is there. In LUMO, easier acceptance of electrons is there. HOMO exhibit higher nucleophilicity, LUMO exhibit higher electrophilic behavior. And examples of HOMO are alkenes. As alkenes are having pi bond, it is rich in electrons. Alkenes contain sulfides, amines. Examples of LUMO are all carbonyl compounds, and carbocations, C plus ions, that is carbocations, and electron deficient alkenes. Mostly it is very important, electron deficient alkenes. As alkenes having pi bond, I have said they will have HOMO, and these are electron rich species. Here alkenes are also act as LUMO, but when they are having electron deficiency, right, when they are having electron deficiency, they will also form LUMO molecular orbital. Most importantly, how the interaction will occur between HOMO and LUMO of a molecule. Electrons, how the electrons flow from HOMO and LUMO, HOMO to LUMO, or HOMO of one molecule to LUMO of another molecule. HOMO and LUMO. You can write like how the electrons will flow from HOMO of one molecule to LUMO of another molecule. If the energy gap between HOMO and LUMO is small, then the interaction is highly efficient. The energy gap between HOMO and LUMO is small. The interaction between HOMO and LUMO is highly efficient. Second one is proper orbital symmetry. You all know that the symmetry, that is B is having dumbbell shape, S is having spherical shape, D is having double dumbbell shape. The proper orbital symmetry is there between HOMO and LUMO, then efficient interaction will occur between the two molecules. The third one is effective overlap. All these three are important in HOMO and LUMO. We can consider an example, that is simplest hydrogen molecule. We all know that it is made up of two hydrogen atoms. One H is having one electron and another H is having one electron, and we also know that electron configuration is 1s1. Here also 1s1. We know the electronic configuration, and hydrogen same molecules where are there. We can discuss the energy profile diagram of H2 molecule, right? This is energy profile diagram. One s orbital of one hydrogen and another s orbital of another hydrogen will combine together to form molecular orbitals, right? This is molecular orbital theory. It will form bonding molecular orbital and anti-bonding molecular orbital. One electrons of one hydrogen and another electrons of another hydrogen will combine to form H2 molecule. According to HOMO-LUMO concept, HOMO is highest occupied molecular orbital. This is sigma and this is sigma star, right? According to HOMO, the sigma will be known as HOMO as it contains two valence electrons. Highest occupied molecular orbital as it contains two valence electrons of the hydrogen molecule. We can write H2 electronic molecular configuration is sigma 1s2 and sigma star 1s is vacant, so empty, right? It is called as LUMO, right? It is called as LUMO. It is lowest unoccupied molecular orbital, right? It is known as lowest unoccupied molecular orbital, right? And also by using frontier molecular orbitals, we can also determine the bond order. Bond order. Bond order is equal to half of number of electrons in bonding molecular orbital and number of electrons in anti-bonding molecular orbital, which is equal to half number of electrons in bonding molecular orbitals are 2 minus no electron is present in anti-bonding orbital, that is vacant in nature, and the answer will 1. Hence the hydrogen and hydrogen are linked by sigma bond with one sigma bond, right? Sigma bond. Like this, frontier molecular orbital will help in the determination of bonding nature and bond order, chemical reactivity. In further examples, we can consider the chemical reactivity, how the bond will dissociate, right? We can consider. Now let us consider the example of reaction NHHH. NH3 is reacting with CHHH CH3I. What will be the product? It is NCH3H, which is having positive charge, right? This will be the reaction. And how the frontier molecular orbitals will help to form the product, we can see in this example. We know that in this compound we have to discuss this compound. Let us consider energy profile diagram of this. Energy profile diagram of this. We know that electronegativity of carbon is small than iodine, right? We know that electronegativity of carbon is 2.55 and iodine is 2.66. Electronegativity of carbon is 2.55 and it is 2.66. A small difference is there between the electronegativity. Hence, energy of the carbon is less, right? And energy of the electronegativity of the iodine is more. So this is for carbon and this is for iodine. So one electron from carbon and another one, the sigma bond is formed with two electrons, right? Another electrons of iodine will react with each other and they form bonding molecular orbital as well as anti-bonding molecular orbital. This is sigma star. Here 2p, one electron reacts with 5p, 1, right? Can write the electronic configuration of iodine as well as carbon. You will be known for that. So the carbon valence electron will react with the iodine valence electron and they form sigma bonding and sigma star anti-bonding molecular orbitals. So now what is the HOMO? What we in here? This is HOMO and this is LUMO, right? Correct? And here the size of iodine is larger than the size of carbon. The Frontier Molecular Orbital Theory will discuss how the HOMO and LUMO interaction takes place, as well as it also discusses the bond dissociation. It will also discusses the bond dissociation. Here, iodine is having more big size and carbon is having lesser in size. Hence, due to steric hindrance, the formed bond is weak. Weak bond has been formed between carbon and iodine due to the size difference, right? And discuss about this carbon and iodine. Here, carbon and hydrogen bond is also present in this compound. The carbon and hydrogen bond is also present, right? Now consider the energy profile diagram of carbon and hydrogen. This is the energy profile diagram of carbon and hydrogen. So carbon electronegativity is higher than hydrogen. Hydrogen is having electronegativity of 2.22 and carbon is having 2.55. Large electronegativity difference is there. So carbon, sorry, this is for hydrogen and this is for carbon, or you can consider uh, this is for carbon, which is having higher electronegativity, and hydrogen is having less electronegativity. The energy difference is high. Carbon is having 2p electron, hydrogen is having 2s electron, right? And they will form together to form sigma and sigma star bonding and anti-bonding molecular orbitals. So this is for carbon, this is for hydrogen, and size of carbon, and this is the size of hydrogen, right? There is no much difference in the size of carbon and size of hydrogen, and it is a stronger bond comparative to carbon and iodine. The carbon and hydrogen bond is strong compared to which bond? Carbon and iodine bond, compared to carbon and iodine bond. Hence, this bond will dissociate when a nucleophile will attack to carbon. The carbon and iodine bond will dissociate, not carbon and hydrogen, right? Now, according to LUMO, this one is LUMO and this one is HOMO. According to LUMO, it will accept the lone pair of electrons. Now, NH3 will directly give the lone pair of electrons to this, and hence this bond will break, right? When nucleophile is attacked to carbon, easily Ci bond will break and the product methylamine will form, ammonia I minus methyl ammonium salt will form. Like this, we can easily determine which is the HOMO and which is LUMO, which is having a weaker bond, which is having strong bond. By the frontier molecular orbitals, we can easily conclude that which one is HOMO, which one is LUMO. In the next session, we can consider more and more examples on this.